in the chat room, and we'll address them after the speakers completed their talk. Okay, so the first thing we want to do is Spencer, are you recording this meeting now?
Yeah, I just started recording.
Okay, sounds good. Okay, so what we want to make sure of is we're going to have our door prizes. So sometime during the meeting, fill out your information for the door prizes. So I just want to make sure that everybody does that. So because we do have some pretty nice door prizes, even though we're just meeting virtually or meeting on Zoom meetings, at least we're getting some door prizes out to you guys. I know all of you guys are the most interested in the door prizes. I know that. Okay. So the next thing we'll talk about is I want to go over the committee reports. I think the only committee we really need to go over right now is the Lockwood Committee, because Ford Observatory is closed. And the Lockwood Committee, I will have Kevin give a little bit of a report on what's happening at Lockwood Valley. Kevin, it's yours.
All right, thank you. Well, everything is still closed down for the general membership. If there are star members wanting to go up, please use the sign-in sheet, just so we know that somebody's up there. And basically, that's it. That's all, folks. The cat's here.
Quick interruptions. For Spencer, I think it might be you because you're the agenda window. For some reason, your second monitor keeps popping in on the left-hand side of the screen.
Okay, I think I fixed that now, hopefully.
Yep, it's fixed.
Okay.
No worries. Just letting you know in case you didn't realize it. Sorry. Go ahead.
Okay, I don't think we need any other committees right now. Of course, Joe Phipps and Spencer are taking care of the merchandising that we sell a lot of stuff on our website to members. And another committee that we are probably going to create at the next board meeting that was brought to my attention, we may want to create a new members committee that will interface with the new members and let the new members know what's going on in the club, so we can at least let the new members know what's going on. Okay, do we have any other announcements that need to be made, that somebody knows that we need to be made?
Just 1 second, I'll get I'll put the link for the door prize on the chat. Here we go.
Okay.
There's a laser.
Alicia, you're the best.
I know.
I see two of the new members that I spoke to are here this evening. Welcome. It's Miles and what was the other one I saw here? Who's the other new member?
That would be Robert, or my nickname Roy Vanderhook, new member.
There you go, and Angela. That's why I talked to Angela today as well. Thank you for all coming.
I'm a new member.
Yay.
Hello.
Welcome.
Hey, thanks for all showing up so quickly. I know you all got short notice, just a day or so. So thanks for coming.
Okay, well, it looks like any other new members out there? I think we've covered our new members. Any other special announcements that need to be made?
I think we're good.
Huh?
Nope.
Oh, okay. Well, I guess we can very quickly go on to our guest speaker, Birley Lewis. I'm going to turn this back over to Spencer, and he can give the introduction for Birley, and she's going to give a presentation on how to image an exoplanet. Some of us having difficulty imaging our own planets, let alone exoplanets. Okay. Spencer, it's yours.
Okay, so Birley is you can, I think I've got it displayed on the screen. So she's a third-year grad student at the UCLA, and she's interested in the complete story of exoplanets and how we can observe them in the process. So she's also a science writer and part of the Astrobytes collection, and she's got an Etsy shop playing with and enjoys playing with a rescue dog. What do you sell on your Etsy shop? I didn't have time to look that up.
Oh, I actually so I make a lot of space jewelry. I'm actually wearing some of the earrings that I made. They're like these hoops that have different gemstones that look like the solar system. And then I also do a lot of embroidery and random textile art when I feel like it. So I'm actually making a rug that looks like my dog right now.
Okay, so the title is How to Image an Exoplanet. And so I guess you can read the abstract as well as I can read it out loud to you. So I think with that, Riley, I'll turn it over to you.
Okay, so I'll share my screen in a second. Before I get started, I want to make a disclaimer. You may hear a dog bark. I have a rescue dog who is really needy, so whenever I'm talking to other people, he gets offended that I'm not talking to him. The other disclaimer is, because of the pandemic, he's the only living creature I see, so if I forget how to speak for a second, it's because I only ever get to speak to a dog. So sorry in advance. But yeah, if it's okay, Spencer, I'm going to take over screen sharing.
Okay,
Is
go
that
ahead.
cool?
Go for it.
Okay. There we go.
Okay.
That should be all good there. All right, can y'all see everything? It should just be a black slide with text right now. Are we good?
Yes, that's good.
Okay, perfect. Well, then we'll get started. So to get started here, I want you to imagine an exoplanet. So when you think of an exoplanet, what do you see? Like, what is the image in your mind? I'll give you a second to think about it, get into detail, really imagine what you would see when you think of the word exoplanet. Okay, hopefully we're forming some beautiful images in our minds, and I would take a bet that the images you've come up with look something like this. So when we think about exoplanets, we often think of these really gorgeous artist illustrations that are used for all of these NASA press releases. So the thing is, when it comes to actually, imaging an exoplanet, so that's a planet outside of our solar system, it's really not going to look anything like this at all, at least not from what we can see in our telescopes right now. So it makes sense that our conceptions of exoplanets look like this, like fanciful versions of planets in our own solar system, because the only reference point we have are planets in our own solar system. And these are what, we're seeing in the NASA headlines. And also these artist illustrations are often based off of solar system planets. Like the one in the upper left here is quite obvious, or sorry, upper right is obviously just a weird colored Saturn. And a lot of them are like strange colored Jupiters. So it makes sense that this is what we see. But what would an exoplanet actually look like through a telescope if we were to take an image of it? And the answer is something like this. So in today's talk, I'm going to tell you about how we actually image exoplanets. And a little bit about me. So I am a third-year grad student at UCLA, like Spencer said. And so what I do actually is work on the technology that we need to image fainter exoplanets, things that are more like Earth. And I'll talk about what we can currently see and what we can't in this talk. So this is a really famous image of a multi-planet system that's been directly imaged, and we're going to come back to this later in the talk. So each lettered dot here is actually a planet. So this is what a directly imaged exoplanet looks like. So first off, why is this such a hard problem? So we know we've discovered lots of exoplanets so far. We've actually discovered, I want to say, around 5,000 already. But most of those were not directly imaged because this is a really, really hard problem. So first off, we have an atmosphere that gets in the way. Second, exoplanets are absolutely tiny in the scale of outer space, and they're very far away, which means they're faint, as a lot of you probably know. And to make things worse, these tiny faint things orbit around really large bright stars. So it's like we're trying to take a photo of a firefly, except that firefly is buzzing around the bright lights of Las Vegas, and we're taking a picture from Los Angeles. So it's like we're here trying to take a picture of this firefly around these bright lights. It's extremely difficult because those planets are so faint and they're getting drowned out by something much, much brighter. So let's tackle each of these problems one by one with the different instrumentation and techniques we have. But first, if it's so hard, why do we even want to do this? Why is it worth it? Like I mentioned, we have other techniques to find exoplanets, like transits, which is what the Kepler telescope did, And that found thousands and thousands of exoplanets. So if we're struggling to image a few, why is it worth it? And the answer is that with imaging, we can find planets that we can't find with other methods. So most of the methods that we find exoplanets by are what we call indirect. So they're looking at the star that the planet is around and inferring that there's a planet there. You're not directly looking at the planet itself. So like for transits with Kepler, you're looking at a bright star and you're looking for little dips in the amount of starlight you're getting from when a planet like passes in front of the star and blocks some of it out. And that's found us a ton of planets, but that's biased towards finding close in big planets. So that's why hot Jupiters were one of the first exoplanets discovered, because they're really close into their star and they're really big, so they block out more of that starlight. But we're interested in things that look like all the different planets in our solar system and beyond. So there's this part of this parameter space where it's these really high mass planets that are really far out, like Jupiters and things bigger than Jupiter, which we call super Jupiters, that we really want to find out more about. And the only method we currently have that can look at these types of planets is imaging. The other bonus is that we can see what planets are made of with direct imaging. We can take spectra, so pretty much taking the light that we're getting from a planet, breaking it up into its component colors, and then looking at where different parts of the light have been absorbed to see what elements the planet is made out of. This is really important for answering questions about how planets form. It's important about answering questions about habitability. So that's one of the biggest questions that people are working on is, can we find a planet that we know is habitable? And in order to know if it's habitable, you need to know what it's made of, if it has water and the right components for life. There are other ways to do this with transits, but it's more straightforward to just do it with spectroscopy where you're directly looking at the planet itself. So that's a big advantage here. Then the last big advantage is we can actually watch their orbits. So the planet system that was in my title slide, HR 8799, this is another image of that. It's a little movie where it's different images from the Keck telescopes in Hawaii, where you can actually see the orbits of these planets. So with other methods, you have to do a lot of disentangling to figure out, what planets are there and what their orbits are. But with direct imaging, it's literally as simple as you can see it. So it's a lot more plain to understand what's going on in the dynamics of these solar systems. And also, it's just really cool to be able to do this. So this is why we want to do it. But let's get back to how we can actually do it. So first off, we got to deal with the problem of the Earth's atmosphere. So those of you that do observing, you probably know that there are some nights where the air is just really bumpy and your seeing is really bad and your image is going to be blurry because of it. So this is a video of the moon through a telescope where you are seeing that atmospheric turbulence that's making the image wobble. So when things are unstable, the image gets more blurry. And since we're looking for things that are such small, faint details, this is really important. We have to get rid of this effect. So to go a little more into this, the reason we have this turbulence is because you've got the light coming into the atmosphere from the star, and you can imagine it as a nice flat wave of light, just like a flat plane wave. But as it hits the atmosphere, our atmosphere is bumpy. There's wind, there's differences in temperature, there's clouds, and all these things are going to change how the light refracts through our atmosphere, and you're going to end up with basically this lumpy wave front. It's no longer the nice plane wave that came in. It's all messed up, and it's going to be blurry, and it's going to be changing with time. So this is what's coming into our telescope, but we really need it to be that nice flat plane wave so we can get a crisp image. So what we do is we fix that lumpy wave with adaptive optics. So this is a big thing at UCLA. The Galactic Center Group is one of the pioneers of this. They discovered Sagittarius A star, the black hole at the center of our Milky Way. Professor Andrea Ghez recently got the Nobel Prize for that. And part of their pioneering work was doing this adaptive optics at Keck. So what is adaptive optics? It's basically fixing that lumpy wavefront. So we've got our incoming wavefront with airs, and then a sensor in the telescope sees that wavefront and measures basically what is messed up about it. And then it tells a deformable mirror that can actually move in response to that how to move so that it can correct for the errors and output a nice flat wave that can then go to our detectors and have a perfectly crisp image. So it's really incredible how well this works. So this is from the Galactic Center group, and it's an example of the difference between without and with adaptive optics. So at first you're looking at one of these stars and it's just totally blurry, but when you have adaptive optics on, you can then actually resolve the stars. So this is important for the Galactic Center, just like it's important for imaging exoplanets, since you need to be able to see that really, really fine detail. So once we've done that and we have a nice crisp image to work with of the star that we're looking at, hopefully with planets around it, we need to deal with the starlight. So it's a way of thinking about it is if you're on a stage and you've got those really bright stage lights in your face, if you want to be able to see the audience that's beyond you, you have to block out that bright light so you can see the fainter things. So to go back to the firefly analogy, if you want to see the firefly, you got to block out Las Vegas. And so the way we do that is by using a coronagraph. So these were originally used to look at the corona of the sun, so the outer layers of the sun. This is a picture of our sun with a coronagraph on top, so you can see those outer layers. And it's really the same idea with imaging exoplanets. You just block out the stars, so you can see the fainter things around it. So this is a simulation of what the solar system would look like from 30 light years away. And on the left, you've got no coronagraph, where we have absolutely no chance of seeing the planets in all that bright glare. But when you have the coronagraph on, then suddenly Saturn and Jupiter pop out. So the way that we would actually be able to see planets is by using a coronagraph. Unfortunately, though, that doesn't solve all our problems because stars are really bright, and even once you block them out, there's still some light left over. So we have to find the planets in that. Also, this GIF isn't playing. That's unfortunate. Had an interactive bit. Well, guess that's not going to work. So this is an example of some actual direct imaging data. So you can see, even though that star is blocked out in the center, there's a lot of light left here. So we call this noise speckle noise. And it's just the leftover light that diffracts through the telescope that's left over, and it's just our noise in this image. In the center, you can see a little hole where the star is blacked out. So if this image were moving, like it is supposed to, you would see that those speckles actually move through this video I'm showing you, where each frame of the video is a different wavelength. So the takeaway is that the noise moves with wavelength, but real objects like planets or companion stars don't. So I'm really upset this isn't working because it's really cool. So I would say if it was showing, look for the planet and then you would see it. There's actually a planet in here that's actually going through the video, because the only way to distinguish it is because it's the one thing that's not moving when all the speckles in the image are. So pretty much there's properties of the noise that we can use in order to distinguish that from the planets we're looking for. And we can have algorithms that will help deal with that. I'm not going to go too into it because it's basically a bunch of really complicated linear algebra and data science. But if anyone's interested, you can totally ask at the end. So once we make a model of this speckle noise to subtract it out, we end up with something that looks more like this. So this is yet another image of HR 8799, the planetary system from the title slide. It is one of the most well-studied direct imaging targets, so that's why it's coming up so often. So since we know that there's a way of distinguishing the speckles from the real stuff, we can make a model of those speckles, subtract it out, and then once you subtract the noise, you have the real planets left. This is only one way of subtracting the noise out of the data. There are a couple other ways. Again, I'm not going to go too into it here because it gets really, really technical really fast, but feel free to ask me about it later. So I've mentioned that although we can do this, and even though it's very difficult, we can do it. And one of the advantages is that we're looking at these really far out massive planets. But on the flip side of that, that's also one of the limitations. So imaging is these green dots here in this image. So those are the planets we found by imaging. So we can only find planets that are at those large separations, that are far away from their stars, because if they're too close into their stars, then the starlight's going to be too bright and it's going to drown out the planet. We can also only see planets that are really large right now, because they need to be bright enough and big enough so that we can see them, within all of that starlight again. And the last catch is that these planets have to be young. So planets like those in our solar system are bright because of reflected light. So that's light that's coming from the sun and bouncing off of their atmospheres. But we're looking for planets that are so young that they're still warm from the heat that was made when they formed. So they're actually glowing on their own, brighter in the infrared. So most of these images I'll show you are going to be in the infrared. So exoplanet imaging right now can find far away planets, so that's tens to hundreds of astronomical units, which is the distance between the Earth and the Sun is 1 AU. We can only find planets that are really large, so multiple times the mass of Jupiter, and we can only find planets that are young. Hopefully, with technology improvements, we will be able to find, some smaller, closer in planets, and I'll talk about that at the end, some future projects that are coming up. But as of right now, this is basically where we are. So what have we found with direct imaging? So far, we have found 51 planets. And if you ever want to get an up-to-date count on the number of exoplanets, you can go to IPAC at Caltech's website, where they actually keep track of all the exoplanets that have been found to date. So this is the Exoplanet Archive from an initiative called NASA Exoplanet Science Institute, or NEXSCI, and they show you the number of planets, like up to the day. It's updated almost every day. And they even sort them by, which method they've been discovered with, their stats for Kepler. It's a really fun website to explore. So this is a big planets through direct imaging, which in the grand scheme of how many exoplanets astronomers have found is not that many, but it's added some really important information that we can't get from other methods. So we found 51 planets. We found brown dwarfs, which we'll talk about in a minute. We found binary stars that we wouldn't have found otherwise, like binary stars where the second star is too faint that it gets blocked out by the bigger star unless you have a coronagraph. And we've also found protoplanetary and debris disks, so the remnants of forming planets. So we're going to take a little tour through some of these discoveries to actually see what all these imaged exoplanets look like. Before we start, I'll often say, instead of saying, oh, we found a planet, we say we found a companion to a star. That's because sometimes they're planets and sometimes they're brown dwarfs or other substellar objects. So a brown dwarf is pretty much the intermediary between a planet and a star. So in this diagram here, we've got the sun for reference. So, our nice G star, it's like right in the middle of the types of stars. It's not the biggest, it's not the smallest, it's pretty average and in the middle. And then there's a red dwarf, which is the low mass end of stars. And then there's these brown dwarfs in between that red dwarf and the planet. So these are big enough that they can fuse deuterium, but not hydrogen. So they're not stars because they can never actually fuse hydrogen in their cores. But they're bigger and warmer and have different properties than planets. So right now, the kind of almost arbitrary cutoff is at 13 Jupiter masses. So anything that is 13 times the size of Jupiter or above is considered a brown dwarf, and below is a planet. So that's why sometimes in direct imaging, where we're looking at the bigger end of the planet's, scale, we sometimes just say companion, because we're trying to figure out whether it's a brown dwarf or a Jupiter. So brown dwarfs are actually pretty cool on their own too, because since they are this intermediary between planets and stars, they can actually tell us a lot about things. So why should we care about these not planets but not quite stars? So they can help us answer questions about how planets evolve as they cool. So brown dwarfs, form, and unlike stars where they're producing energy throughout their lifetimes, they're actually just getting cooler. And then they can also help us learn about how stars form. So because brown dwarfs are this intermediary, we can kind of see, what's the difference between a low mass star and a planet forming? they're this bridge that helps bring together these two otherwise very separate, ranges of size. And brown dwarfs are easier to observe, their atmospheres and what they're made of because they are bigger and therefore brighter. So they can help us figure out like what's going to be going on in exoplanet atmospheres and like how can we observe clouds. So because brown dwarfs were easier to observe, they're almost like a practice run for like figuring out how we might be able to observe and characterize exoplanet atmospheres in the future. So the first discovery that I wanted to talk about is 51 Eridani B. So this is the direct imaging so far. So it's 2 times the mass of Jupiter. And in this video from the Gemini Planet Imager, you can actually see it moving along in its orbit. I think this one is so cool. So this 2 Jupiter mass planet is the smallest, coldest thing we've imaged so far. And we imaged it using an instrument called the Gemini Planet Imager. So this is an instrument that is dedicated to just planet finding, just direct imaging. And it is in the Gemini Observatory in Chile. So this is actually what my advisor and I are in this group here at UCLA. And I'm actually working on a Debridus right now that was imaged with the Gemini Planet Imager. But we'll talk about Debridus in a little bit. So the Gemini Planet Imager is a dedicated planet finding instrument in Chile that took this image. So pretty much as we go through these discoveries, I'll show you the planet that was discovered and then also the instrument that discovered it. Just because I think that's pretty cool. There's actually a wide range of different telescopes and different instruments that can do this kind of work nowadays. So our next observation is this very important system in direct imaging, which is HR 8799, planets B, C, D, and E. So this one can be thought of as like a scaled up outer solar system. So each planet is multiple Jupiter masses, and each of these is double the distance of Jupiter, Saturn, Uranus, and Neptune. So it really is just like you took those 4 outer planets and then scaled them up. So this is a really well-studied system. We have data on it going back for quite a while now. And so people are looking at cool things like, oh, how have, the compositions of these planets changed over time? Like how have their atmospheres changed? And there's still a lot of really interesting work being done on this. Bonus, the longer we observe it, the more complete orbits we have, and maybe we'll have more of a full circle at some point, which would be awesome. So these images are actually taken with the 10-meter Keck telescopes at the Keck Observatory in Hawaii. So here at UCLA, we have a very special relationship with Keck because the University of California is, very closely tied to Keck Observatory. So this is where, like, the Galactic Center group, found Sagittarius A star. This is where they did all their pioneering adaptive optics work. And this is where a lot of cool planet finding science is going on right now. So Keck is in Hawaii. It's got these famous 10-meter telescopes that are on the mountain. And it is a very cool place that does a lot of planetary work. Our next discovery is Kappa Andromedae B. So this is one of those planets that's so big that we're not 100% sure yet where it is on, that scale of planet and brown dwarf. It's like straddling the line. So in this image, you can see there's the blocked out star in the center. This circle is Neptune's orbit to give you a sense of scale. And then this big thing way out in this planetary system is Kappa Andromedae B. So because it's about 13 Jupiter masses, it's right on that borderline between planet and brown dwarf, which is actually really interesting, again, because it's one of those objects that kind of, blurs the lines between our definitions, and will have to help. It will have to make us investigate more to figure out, like, okay, how did it form? How does it fit into this whole picture of like brown dwarfs and planets? And this one was discovered by the Subaru telescope and a facility known as SCEXAO, the Subaru Coronagraphic Extreme Adaptive Optics. So this is the telescope itself. This is in Hawaii, but it's actually run by the National Astronomical Observatory of Japan. And it's like really cutting edge adaptive optics. So making sure our images are like as stable and clean as possible is still one of the big keys to, imaging exoplanets. So there's an example of like, SCIXAO off, SCIXAO on, showing just like how much clearer this image is. All right, now we're moving on to the debris disks part. So we've actually been able to take images of a planet within a debris disk. So the debris disk was imaged with one instrument, but then we found a directly imaged exoplanet that was actually within that debris disk. So this is Beta Pictoris B. So this outer part here is the debris disk, which is a bunch of dust that's left over from planet formation and from little planetesimals or like fragments of forming planets just smashing together to create rocky dust. And then way within there, there's Beta Pictoris B, which is actually a planet that's formed there. And its orbit is just about the same orbit as Saturn's around the sun. And what's cool is we've been able to observe this system for long enough that we've actually seen Beta Pictoris go from one side of the star to the other. So the image on the right is two different images of Beta Pic and its debris disk superimposed on each other, with a little circle drawn for like the orbit. So this was it at one observation, and then we actually saw it go all the way around to the other side of the star in another observation. And that was taken with the Very Large Telescope, because astronomers are super good at names. So the VLT is a series of 4 8-meter telescopes that can actually be used together for what's called interferometry. And it's run by the European Southern Observatory, and it's located in Chile. So that is another cool planet finding machine. And now we've got a debris disk that doesn't actually have a planet in it. So this is a debris disk that's kind of been referred to as the Eye of Sauron in different, popular coverages of it. But it's really cool because it's this very like crisp, like ring of a debris disk that we can see. So some of the pictures of debris disks are just cool to look at, but there's also a lot of science that can be gleaned from them. Like, why is this such a clean ring? Like maybe there's a planet like shepherding some of that dust in, like what's going on. So there's a lot we can learn about planet formation from analyzing images like this. And then there's another debris disk that's actually known as the Eye of Sauron in popular media too, because people like that comparison. But this one actually has a forming planet inside of it. So this is Fomalhaut B. You can see the zoom in of this little planet here within this big debris disk. So this is pretty cool. We're actually seeing like a dusty forming planet inside of a debris disk. And then a really recent discovery is PDS-70b. So this is like an even younger forming planetary system where this bright blob here is the embedded like forming planet in this ring of dust that is forming the planets in this planetary system. So there's a lot of really cool stuff that's being done with direct imaging already, and there's also a really exciting future to look forward to. So what comes next in all of this? How do we image planets that are, more like Earth? Like, how are we going to actually be able to like take a picture of, an Earth or something that might be habitable? There are 2 ways that people are going about this. One, there's some exciting new space missions coming up. Yeah, someone put James Webb in the chat. That's going to come up. Basically, if you're talking about the future of astronomy, James Webb comes up. And the other thing is new, bigger ground-based telescopes. So one of the reasons that space telescopes are such a big advantage is because going to space gets us away from our pesky atmosphere, and then we just don't even have to deal with that whole atmosphere problem. Like adaptive optics, not an issue. And then bigger ground-based telescopes are great because they give us better resolving power to see faint things. Because the bigger the telescope, the more light you're collecting and the more you can do. These are basically the 2 avenues for future improvement right now. So a quick rundown of some exciting upcoming space missions. First off, like was said in the chat, the James Webb Space Telescope. So in theory, this one is launching at the end of this year. I think it's in October. I say in theory because it's gotten pushed back a lot already. There were problems with the star shade for a while. There's been a lot going on with this, but as of now, even though its March 2021 launch date got pushed back because of COVID, now it's supposed to be launching. The target date is October 31st, 2021. So that'd be super cool if that happens. So James Webb has a 6.5 meter mirror, which is really big for a space telescope. So for comparison, Hubble, the one that got us, basically every fantastic image we have now, like example, my background is the Hubble Deep Field. Hubble had around a 2.4 meter mirror. So James Webb is significantly larger than that. And instead of looking in the optical, it's looking in the infrared, which is where we want to be looking for imaging these planets. So looking in the infrared is good for looking at dusty things. And it's also good at looking at far away things. So things that are, redshifted or like really early in the universe. But that's not quite the planetary science we're talking about. James Webb has a lot of different applications though. But the really big, exciting planetary science with James Webb admittedly isn't actually direct imaging. Like James Webb's thing is going to be transit spectroscopy. So looking at the, why are you licking my feet, puppy? So transit spectroscopy, it's going to be looking at the atmospheres of exoplanets through transits, not necessarily through direct imaging, but it will have two different coronagraphs that could be used for imaging. So James Webb has a ton of different applications. Some of them could totally be imaging exoplanets, but that's not like one of its primary missions. Instead, there's WFIRST, or actually now known as the Nancy Grace Roman Space Telescope. But that acronym is admittedly harder to pronounce. That should be launching in the mid-2020s. And this one, actually, one of its big focuses is its coronagraphic instrument. So it's going to be the same size as Hubble, so it's not going to be like a huge different thing. It's more like tried and true technology. And it's got two different instruments. There's the wide field instrument that can show 100 times larger of a field of view than Hubble, and the coronagraph, which hopefully should be able to see planets that are 1 billion times fainter than their stars. So right now, the things that I've already showed you, we're doing about in the millions. We can see things that are around like 1 million times fainter than their stars. But to see Earth is around 10 billion times fainter. So WFIRST is better than we're doing now, but not quite all the way to seeing other Earths. What we would really need for that is something big and different and game-changing, like Lubar. So the next two missions I'm going to talk about are just mission concepts. So they're not actually like funded, going for it NASA missions yet. So if you want these to happen, make sure to tell your Congress people to fund NASA and stuff like that. So Lubar is one mission concept that's been proposed to launch in the 2030s. And Lubar is basically like Hubble, but like bigger and better and just absolutely a behemoth of a telescope. So if we've got the 2.4 meter Hubble Space Telescope mirror, that looks pretty small compared to James Webb. And Lubar makes both of those look like they are absolutely tiny. So the proposed mirror for Lubar would be around 15 meters, which is huge. So that would be able to do some absolutely bonkers cool science. So Lubar would essentially be the next Hubble. It's a bigger version, but it's doing all the multi-wavelength astronomy. So it's called Lubar because it's the large ultraviolet, optical, and infrared telescope. So those are like three of the three big wavelengths we want to look at, and it would do all of them. It would have that huge 15-meter mirror. They do have a plan B in case that's too ambitious, which is 8 meters, still bigger than James Webb. And it would have a coronagraph with a goal of finding Earth-like exoplanets. So the image here on the right, in the top, is a simulation of what Lubar looking at our solar system would look like. If it was looking at a solar system like ours far away. So with Lubar, you'd be able to clearly see planets as small and close in as Venus, which is wild. And then a bonus is it could also do really cool solar system science. So for example, if we're talking about life in our solar system, the outer solar system moons that have, plumes of water ice and stuff like that are of great interest. So the image on the bottom here is comparing what Enceladus's plumes look like from the Hubble Space Telescope compared to what Lubar would see. Lubar is actually resolving these surface features, which would be super cool. So this is still a mission concept. It's not, officially like green lighted or anything yet, but if it happened, this would be a really, really cool thing and would probably also be the thing that helped us find biosignatures or signs of life on other planets. Another wild mission concept is HabEx. So this is what it sounds like, habitable exoplanets. That's what this mission's goal is. And this would also be planned for sometime in the 2030s, which sounds far away, but that's next decade. It's actually not, it's shockingly close. So HabEx would have this big star shade, which is the thing here. And that star shade is pretty much like a coronagraph, but outside of the telescope instead of something within the telescope's optics. So this mission isn't, you know, like one of those big workhorses that does a bunch of stuff in astronomy. This is something with a very specific goal. It is a planet finding mission. Like it would be able to do other things, but its goal is finding habitable planets. It's a 4-meter telescope, so it's not huge, but it would have a lot of capabilities. Like it would have a coronagraph within the telescope, but then it'd have a different mode for observations where you'd be able to use this star shade that's orbiting outside. So the picture on the bottom is how the star shade would unfurl in concept, which I think is super cool. It's inspired by origami. And the whole point of this mission would be looking for habitable Earth-like planets. So again, this is not something that is like, you know, being built yet, but it is in the like concept design phase and is being proposed. And there's also some cool things happening on the ground. So in the next few decades, we've got the next generation telescopes, or what we call the ELTs, the extremely large telescopes. So our current major planet finders are the Keck telescope in Mauna Kea, the Very Large Telescope in Chile, and then the Gemini telescope, Gemini South telescope in Chile as well. So that's these little mirrors. And then for comparison, these are the mirrors of the proposed extremely large telescopes. There are 3 major ones, the 30-meter telescope, the Giant Magellan telescope, and the European Extremely Large Telescope. So the 30-meter telescope, or TMT, is planned for completion in the late 2020s. And this one would, it's a partnership between multiple countries, so the US, India, China, Japan, and Canada. And its location is Mauna Kea. TMT has had a pretty rocky start so far because of concerns over like Hawaiian culture and the lands on Mauna Kea. So in a way it's good because that prompted a much needed conversation about how astronomy, you know, interacts with indigenous peoples. But the future of TMT is also kind of uncertain right now. But there are also other projects for ELTs going on, and hopefully this will still be completed sometime, even though it may be in a different place than Mauna Kea. The Extremely Large Telescope is the European version of this. So this is created by the European Southern Observatory. This is an artist rendering. All of these are, they're not built yet. So this one would be also in Chile in the Atacama Desert, where a lot of other telescopes are. And its planned completion is around 2025. And the Giant Magellan Telescope is another international partnership of the US, Australia, Brazil, and South Korea. And it would also be in Chile. And it would, in theory, be completed in the late 2020s. So these ELTs, because of their extremely large size, would be able to get us really amazing resolution that would help us push towards imaging more planets, and also just doing so much more astronomy. So the rule of basically the history of astronomy is like whenever you have a big increase in telescope size, you find a bunch of things that you didn't expect to find before. And plus, we're always working on better technology for the telescopes we already have. For example, a group at Caltech and some of the people that I work with at UCLA, they're working on a new instrument for the Keck telescopes called KPIC, the Keck Planet Imager and Characterizer. So we're taking the existing infrastructure we have and applying new technology for detectors and for adaptive optics and other optical things in order to do more science with the facilities we already have. So there's really a lot to look forward to when it comes to exoplanets, whether that be imaging or other methods or finding life. And the next few decades are going to be a really exciting time, and we're already taking pictures of so many exoplanets out there. So that's pretty much it. I would love to answer questions, and I hope you learned something cool today.
Totally awesome. That was great, Birley.
Amazing.
That was really cool.
Amazing.
Okay, fantastic talk. Do we have any questions?
What got you? I do. What got you into this, Briley? Of getting into exoplanets like this? I mean, what got you to this point? And that I guess what I think you know what I'm saying. What pushed the button that say that you really wanted to do this?
Yeah, there's a couple facets to that question. One, the reason that I'm in astronomy is because I think it's kind of a funny story. I always wanted to be a veterinarian when I was a kid because I love my dogs more than anything. And then I had to cut open a frog in school and I couldn't do it. And so I was being the very type A child that I was like, oh my God, my dream is dead. Like, what am I going to do now? And one of my friends gave me one of Neil deGrasse Tyson's books and I read it and I was like, I like that. We'll do that. And then I just kind of stuck with it because it always ended up being something that I found interesting no matter how much more I learned about it. And then when I was in college, it was, every class in college is hard, but I could take my physics classes and be like, this is terrible because it's, pain and suffering because that's what physics classes are. But at the same time, I still like it. So I knew I was doing the right thing. Yeah. College physics is like not a good time, but at the same time, I was still kind of having a good time. So I knew that was a good sign. And then the reason I got into exoplanets is because the other reason I thought astronomy was cool is because I'm a huge sci-fi nerd. And the kind of sci-fi that I always loved reading about was exploring different planets. And it turns out that with the fairly new field of exoplanets, that's basically what we get to do is, just discover all these different worlds. We might not be going there in a spaceship or stepping through a Stargate, but we get to characterize all these different worlds from the ground, which is bonus because I actually don't like flying or heights. So I get to do it all from the safety of a telescope.
A couple questions, just real quick, real fast. Can astronomers like our club is there a way we could see these images or be able to tap into a website or something that is fresh and new?
Yeah, I think the best source for that is probably the website that I showed that had the planet counts, Nexi. So this is something that's run by Caltech. It's I'll put it in the chat. So they maintain a database of whenever there's new discoveries, they add them to their list. There we go. Next slide. That they maintain a database of all the exoplanet discoveries. So I think that would be a cool place to look. And then I mentioned I also like science writing. I try to make sure to write about new things when they come out. And I'm hoping that, people will start writing more publicly about their discoveries in addition to writing, scientific papers about them.
Hi, Birley. Thanks for a great talk. I have a couple of questions here. First is, how long does it take to image exoplanets? I mean, I assume that this is probably much quicker method than the transit method. But I believe in transit, you have to wait long time to determine the period of the planets and all that to confirm the planets. But imaging is probably much faster. But I would still think it probably takes quite long. So just to get an idea, how long does it take to image a planet? And how do you go about, say, okay, maybe this star may have planets. Do you already have an idea that this star may have a planet or through some other means, or you just go random or try your luck?
Yeah, so I'll answer the first question first. So first question is, how long does this take? So the actual camera exposures are usually a few minutes. So it doesn't actually take that long to get an image, which will, help you figure out if there's a planet there. But if you see something, you need to follow it up to make sure it wasn't just a weird speckle that looked like a planet. So you have to take multiple images over a period of time to make sure that it is a real planet. And then if you're pretty sure it's a planet, you still have to take more images to make sure you can see it move across the sky, to make sure that it's actually something that's bound to the star that you're observing. There have been cases before where people have seen something that's oh, that might be a planet. And then when they go to follow it up, they realize that it's moving in a way that it couldn't be orbiting the star. And it turns out to actually be a background object that's just in the image. So it still takes a while. So you still have to take months to a year of data to be really sure. But at the same time, you could see something in an image and be like, oh, it looks like a planet, and have an idea that it's there with one image. It's just the follow-up to make sure that it actually is like a bound companion that takes longer.
Riley,
And then,
So what's
Yeah.
the probability of success so far? Like, okay, you take multiple images of many stars and then say, oh, this looks like a good candidate. So is it a good good
yeah,
yield?
so
I would say.
to finish your second question, the second question is, like, how are you choosing targets for these? So it depends.
Right.
In the beginning, when people first started imaging exoplanets, they just did blind surveys of nearby stars, where they just looked at, hundreds of stars and tried to find what they could to come up with, how common these big planets are in the first place. It turns out they're not actually very common to have these really big planets really far away from their host
Right.
stars. So the yields are not spectacular, but people have still found things. And then people have started doing, like more clever ways of looking for these exoplanets. So using, hints from other methods that there might be a bigger outer planet there. So like the radial velocity method, where you're looking at the redshift and blue shift of a star wobbling around its center of mass. Sometimes you see like little trends in the RV signal that might signify that there's an outer planet that's like, exerting an additional tug on the star. And so people have used those radial velocity trends to say like, okay, now I'm going to go try and look for a directly imaged planet there, and then they find it, which is cool. And people have also, done similar things for looking for debris disks, where they look at stars where there's too much, like more infrared light than expected from a star, because that usually signifies like dust. And so then they go try to image around these, two infrared stars to see if there actually is a dusty disk around them. So yeah, there's two ways. There's like blind surveys, and then there's using other clues to, find more planets, because the occurrence rate of these types of planets is pretty low.
Riley,
Follow-up
kind
question
of
was
a
like,
follow-up to what Nasir was saying.
Yeah.
In two things. First of all, one of the things I noticed in one of the shots that you were showing, where you had, I think, the 4 planets, the big image you kept showing, that was taken over 6 years.
Yes.
Okay, so the motion that we were seeing over that 6 years was not what we would anticipate as what I would call an annual loop in real time, right? I mean, for us, or is that particular area, is it that slow for a planet to, circumnavigate its sun?
Yeah, it's just that they're far out, so their orbits are really slow. So like, the orbits of our outer planets can be multiple years, like multiple Earth years. So the further out the planet is, the longer its orbital period is. So we're, 6 years is actually like how long it takes it to make that loop, just because they're really far out from their host stars.
Oh, okay, because it never actually made the loop. It just moved a little.
No.
So that means it
Yeah,
literally
exactly.
could have been a 25 or a 30-year
Yes,
loop for
exactly.
a full. Okay. Secondly, this is a silly question, because most of us have telescopes that look at a certain field of view. What is the field of view on an image like that?
Very small. Very, very small. Very
So a couple of
small.
arc seconds, right? So nothing
Yeah.
nothing that any of us are going to see with our
No.
stuff.
No, so these are like very tiny, narrow fields of view. Yeah.
Okay.
Yeah, you are correct.
Riley, thank you very much for the awesome talk. When I heard about the topic, I got very excited, because just in the past week, unless I dreamt this, but I'm pretty sure I actually heard this in real life, there's a proposal, nothing that's going to be flying anytime soon, but a proposal to put something out at around 90 AU, which would have a chronograph and would use gravitational lensing in order to image exoplanets. Have you heard about that?
I have not actually. I admittedly don't hear much about lensing. I'm just not super in touch with that part of the community. But that's cool. I'll have to look into that.
Right, thank you.
Bradley, another question, or my follow-up question was, is the exoplanet imaging done normally on a nearby planet, or doesn't matter the distance?
Yeah, so they're all pretty nearby. So that's true of basically all the exoplanets we've found. They're all pretty nearby stars.
Okay.
Because in order to be able to see these things in that much detail, they have to be pretty close, like whether it's for transits or anything. So
Right.
yeah, there's a really great diagram. I can't remember who made it, but there's a diagram of like the Milky Way, and there's like this tiny little dot that's like, here's the entire area we've surveyed for planets. It's not very big. Because all
So
these things are
I
so
mean,
hard to find, whether it's
comparatively,
from RV or transits or.
so compared to transit method, does it have to be even closer than transit method to image planet? I would think it would be even.
I
Has to
think
be
so.
even closer.
I'm not sure exactly the range of each of these. One
Uh-huh.
of the
Okay.
limitations of direct imaging is that these stars actually need to be bright, which sounds counterintuitive because the brighter the star, the like fainter the planet's going to be in comparison to it. But in order to use adaptive optics, the stars have to be bright enough for the AO system to work. So we actually
Right.
need to use bright stars. So there's a lot of limitations right now and a lot of technical challenges that make this a really hard method. But people are working on it every day.
Okay. Thanks.
Riley, I have a question. I'm so sorry. Could you elaborate on adaptive optics and basically the computational photography behind it?
And to
Yeah,
add to that,
so
to add to that, actually,
Mhm.
we have adaptive optics available to us for our telescopes.
Oh,
Is that
cool.
the same thing as what you're talking about? Go ahead.
I don't know what AO is available to telescopes that aren't major observatories. I always joke that I'm a bad astronomer because I don't actually go outside and look at the night sky very often because I get cold very easily and I don't like to be up late at night. Like this is basically my bedtime. So I'm that terrible astronomer who's like 9 p.m. night, bye. And I don't stay up to look at the night sky. I'm like, I like thinking about it. I don't like being outside in the cold. So I admittedly don't know what's available to like backyard astronomy. So I am not sure on that. There are two kinds of adaptive optics, and I did only talk about one kind here. So one kind of adaptive optics is using a laser guide star, where you actually shoot a laser off into space and then see how the laser has fluctuated. The way I was talking about that's usually used in direct imaging is natural guide star AO, where you're observing the star that you're going to look at, and there's a sensor that's in the path of the light that's going to sense what's going on with the light and then correct the mirror. So yeah, to answer the second question, I don't know what's available.
But you're still
y'all right
dealing.
now.
But Riley, you're still dealing with sensors. You're still dealing with okay, that's what I was trying to get at. I didn't know whether or not it was
Okay,
in the
cool.
optics in the glass itself. Do you see what I mean? Or in
Yes.
yeah.
Yeah, no, these are optics that are like it's stuff in the optical path. So like there's a sensor that's gonna, measure the incoming wavefront. And then there's the deformable mirror itself that is like an actual mirror, it's like a bendy mirror with actuators behind it.
Well, that's
where
what
the
I
actuators
saw.
poke up the mirror in different places. Yeah.
That's what I saw. That graphic, that the mirror looked like a topographical. Yeah, and that's what kind of I needed to ask you about that. Is there a rough surface as such? Like a
so it's not really.
Yeah, I'm sorry.
It's not necessarily rough, like the mirror is still smooth so it can reflect properly, but it is deformable in shape such that it can correct the wavefront so that it flattens out, if that makes sense. So it is actually a mirror that is essentially bending. It's not the graphic was obviously very exaggerated to prove a point.
Yeah.
But yeah, it is actually a mirror that is bending. I mean, it's a smooth mirror, but it's bending. Also, I see Tim in the chat says amateur AO is just tip tilt. That would make sense. So the things like that deformable mirror that I mentioned are really advanced and really expensive. But then there's other things in the optics that help correct the image, like a little tip tilt mirror can help with like the biggest corrections. But in order to get the really fine details, you have to have something more detailed like a deformable mirror.
And that's what I was asking about was the fine. I know tilt shift, of course, yeah.
Nice. Okay, cool. Awesome. Yeah, apologies. I totally don't know what like the state of the art is for like, you know, other observing telescopes.
Yeah.
Like I said,
Yeah.
I'm not a nighttime person.
Yeah, that's pretty good.
David, you're on mute.
Thank you.
Oh, I was gonna say something too.
I was saying Tim Thompson had we had a lecture at over at Griffith that talked about the adaptive mirrors, right, Tim? Do you remember what his name was?
That was Claude Plymate from Big Bear Solar Observatory. He just retired last month. But they have adaptive, all the solar telescopes now have adaptive optics, and they have an AO system and a multi-conjugate AO system, because the location of your flexible mirror and the light path can be correlated with an altitude in the atmosphere. So you can put multiple flexible mirrors in and then correlate to the scene correction at different altitudes. They only do 2 right now, but someday some bright guy will figure out how to do 10 or 15 and drive everybody completely nuts.
Yeah, some of the advances that are going on with AO are really wild right now. Like really wild technological advances in like software too. It's amazing stuff.
I think that was my reason for jumping in with the question about the AO, because we have the availability to purchase an AO adapter to put in front of our cameras, but it is nothing like you're describing with a laser adapted distance with a flexing mirror. It's purely just modifying things a little bit for the lower angle of attack when you're nearer the horizon and trying to image. So I think for a lot of us amateur imagers, your description of AO was something out of league for us.
Got it. That makes sense. Yeah, the stuff that's on major observatories like Keck is like multi-million-dollar, like absolutely bonkers stuff. So
yeah.
Oh, I'll pick one up tomorrow.
That'd be great, wouldn't it?
Yeah, we'd like to see you move that one around.
Thomas Hendricks had a question for Birley, I think, in the chat too.
It was about the coronagraphs. A good question.
Yeah, it's a really good question.
Oh, okay, I see it. It says, where is the coronagraph occulting disk in the optical path of a large telescope? Does it have a separate tracing device, or does it depend only on the telescope tracking? Okay, so the coronagraph in the optical path of a telescope, let me think about this. It's after the AO. I wish I had put a diagram of one of these instruments in my slides, because it would be a lot easier to show than to explain. It's towards the end before the detector. So basically the way that this is usually set up is like in a telescope, you've got the AO system that is like one instrument that operates usually separately, because it's used for, multiple different kinds of observations. So the AO is the first thing in the light path. And then basically at the end, you're going to have the actual like self-contained planetary imaging instrument, which is going to have the first occulting mask, then a LEO stop because they're LEO coronagraphs, and then everything else like the detector, and like some of these are integral field spectrographs, so that all comes after. So it's towards the beginning of the instrument, but the instrument is sort of at the end. Does that make sense?
I got that.
Okay. And then does it have a separate tracing device, or does it depend only on the telescope tracking? Usually there is the ability to like move it a little bit if you need to adjust it manually. But like the main tracking is the telescope tracking. Yeah.
Cool. Thank you.
Yeah.
You said you had experience with the Hubble Deep Field. So what did you do with the Hubble Deep Field?
Oh, I didn't. I just said I had a background.
Oh, I thought you. Okay.
I didn't mean I have a background. I mean I literally have a background.
Okay.
Yeah.
I thought you were too young
You're
for
like
that.
that one.
Yeah.
Come on, Tim.
No. No, the only, so other than exoplanet imaging, the only other thing I've worked on really is I spent some time with the New Horizons mission that did Pluto science.
Wow.
Great
How many
talk,
people?
Briley.
Thank you.
Just out of curiosity, what area of research are you pursuing for your dissertation?
Yeah, so I haven't actually decided on a dissertation topic yet, because to be honest, everything's just kind of like a little bit behind because of COVID. Like we had to push back my master's exams because it was supposed to be in March of 2020, so that was a good joke. So yeah, I haven't decided on my dissertation yet. So far, one of the things that I've worked on in grad school has been coming up with a new data processing algorithm for this kind of exoplanet imaging data, that we weren't sure if it was going to work, but it could work. And it turns out it works a little bit. So I'm finishing writing up the paper on that. Basically would need like a lot more computational work to make it actually like, implementable. But I think it kind of works. But that's not published yet, so that's basically all I'm going to say on that. And then I'm working on a debris disk that was imaged by the Gemini Planet Imager, and trying to model it to understand what's going on, what the disk is made of, that kind of stuff. And then last year I finished up the last project from my work with New Horizons, and that paper's finally out. And it was about the movement of the nitrogen ice on Pluto as the seasons change on Pluto. So Pluto's mostly nitrogen ice. So I did a study using like the New Horizons data to see where the nitrogen was when we did the flyby and what might happen to it in the next couple decades. So yeah, that is a sampling of the things I've worked on so far. We'll see what my thesis is going to be on, because I don't know yet.
You know what the debris objects are made of, or what their makeup is?
Yeah, typical astronomical dust. So like different kinds of like silicates or carbon, and there's not really. So when I say debris disks, that means that most of like the gas has been like blown out of the disk, and you're just left with the the remnants of when rocky planetesimals collide. So yeah.
What kind of dog do you have, by the way?
I have a husky border collie mix. He's a senior that I got as a rescue at the beginning of the pandemic. So I got him when he was 8 and he's now 9. And he is the absolute joy of my life. He's the sweetest thing.
Yeah. Awesome.
One more question. You talked about doing some noise processing when you take the multiple images and then reduce noise. So is that the basic idea is like stacking, that the way we do this, take multiple images and then reduce noise, or there's some other special algorithm used to remove the noise?
Yeah, so it's actually not stacking. So you can't average out this noise. It turns out that the noise that's left over in high contrast imaging, which is like this exoplanet imaging, is like the worst pain ever. It would be so awesome if it averaged out, but it doesn't, which sucks. So the algorithms that are mainly used to do this are based in something called principal components analysis. So if anyone has taken linear algebra, it's like you're taking an image and breaking it up into its eigenimages. So it's like principal components, and then using those to reconstruct an image that's just the noise. In not horrifying math terms, like I personally did not like taking linear algebra. The idea is, so if you have an image, you can break it up into like the most important parts of it. So like the different, shadows and things like that. And the way it works with these exoplanet images is, like I said, the noise has certain properties that the planet doesn't. So if you construct your principal components just right, you can make it so that the most important components of the image are the noise, and the planet is like way at the end of the list, so it's not going to get taken out. So you're basically like taking these first components of this image and subtracting those out and leaving the rest, and the planet is in the rest. So yeah, it's like fancy linear algebra tricks.
Okay, so it's more like characterizing
if there's anything
the
I've
noise
learned.
itself. It's like characterizing the noise itself. It's not really something random. I guess it's
it is stochastic,
model,
but
create a noise model or something.
Yeah, so you're creating a model of the noise from the noise itself.
Right.
Yeah, it's. I should have put extra slides in my talk to explain it because it makes so much more sense once you see a few pictures. But yeah, it is definitely more complicated than just stacking. Yeah.
But okay, I'm going to jump in here on the noise issue again. Isn't there some level of randomness to the noise that dithering your imaging might allow you to erase the same way we do in our multiple images?
Not really. So the things that are left after high contrast imaging are these things we call quasi-static speckles. So pretty much they're not going to actually move that much in the image because of the optics are set up. So unfortunately, like they're not going to average out because they do move a little bit, but they're not truly random. They're going to be in certain spots of the image. So no, the randomness doesn't really help too much on this front, unfortunately. It's a shockingly hard problem. Like that's actually what I spent the first 2 years of my PhD on, was trying to come up with a new data processing algorithm for that.
Is it something similar to what they used to image the black hole?
No.
Okay.
That was are you talking about the Event Horizon Telescope?
Yeah, no, but the kind of data processing they used to image.
Yeah, no, super different. So they did interferometry. This is a very different kind of data processing. Yeah.
Okay.
Riley, in the spectroscopy analysis you were talking about, where the light of the sun is like coming through the image of the planet, and you take a spectrum, or were you talking about a direct spectrum of the planet?
A direct spectrum. So
okay,
like,
and then you said you could tell what the planet
photons
was
coming
made
from that
of.
planet.
Like, how can you tell what a planet
so by
is
doing
made of?
spectroscopy.
Like, I can see you could figure out what the outer parts of it might be made of, but how could you tell the?
Yeah, so you caught me. I omitted something. So we're talking about these like gas giant planets. So it would be mostly the outer layers.
So light shining through the gas of the outer layers. But when you say you can tell what the planet's made of, that's sort of limited to.
It's the atmosphere.
Okay, got it.
Yeah, it's the atmosphere. But when we're talking about direct imaging, so when you're talking about spectroscopy for transits, you're talking about starlight that's coming through the exoplanet atmosphere and then continuing onto the telescope. When we're talking about direct imaging, for the most part, we're talking about light emitted from the planet itself. So like there's the actual heat of the planet, and it is.
So it's actually not like in when we think of imaging planets, we're all talking reflected light here in our solar system, but you're talking about these things are big enough to actually glow with their own radiation.
Yes, exactly. That's why we need young planets. Eventually, hopefully with things like Lubar, then we'll move into the reflected light territory, but right now we were at self-luminous planets.
So is it in the infrared?
Yeah.
Okay. Planets don't shine in optical, they only shine in infrared.
Well, then they would. I mean, are some of these planets so big that they're getting close to protostar? Is there some kind of continuum in there? Like it's almost
that's
a
the whole
binary.
brown dwarf things, where it's like brown dwarfs are that intermediate, and that's part of why observing them is so interesting. Is because when we're looking at these objects that are like at the threshold between, like planet, brown dwarf, planet, we're like really understanding that spectrum better. And like, is it a continuum? Are there like harsh breaks? What's going on there? Like, are our classifications arbitrary, or is there something that's really like a clear physical distinction?
Okay, do we have any other questions, or are we completed? Briley, that was a fantastic talk on being able to image things that we astronomers here on Earth have difficulty imaging our own planets, as everybody can probably can say about that particular thing. Now, the other thing is, was there any other questions at all for Briley?
Just one comment from out here over the mountains and far away is that was a fantastic presentation. You get both thumbs up. And yeah, I've had my close encounters with adaptive optics. And I believe that, I think Tim said it all, the amateur adaptive optics are just compensating for image motion and not even coming close to wavefront correction. Unless you're very well healed.
We're rich.
Yeah.
Man.
A quick question, Briley. How many people are working on this at UCLA with you? Is it just you, or I mean, do you have a group of people?
Yeah, I'm working with Professor Mike Fitzgerald's research group, and we're all working on kind of like different aspects of these problems. So there's a couple of us grad students that are working in this group, and we've actually got some undergrads too. And basically everyone's working on like different aspects of, imaging and infrared instrumentation that kind of all serve this greater purpose.
Wow, you are the future. Thank you so much.
Thanks. Thanks. I appreciate it. Thanks for being a great audience, everyone.
Okay, well,
everybody,
thank you. Spencer, are we ready for the next segment of our meeting, the door prizes?
Yeah, so I've just posted, I'll repost it again, just the link for the drawing. Right there. So go ahead and enter your name in the drawing, and we'll go through and I'll give everybody about a minute to get it in if you haven't. Let's see, we have right now 39 people are still here, and we have, let's see, 25 entries for the drawing. So still a few seconds, about a minute or so, get yours in. So while we're doing that, Alicia, you want to talk about the prizes?
Sure. Let's see.
Put you on
Not
the
much
spot
to
there.
say. Put me on the spot, right? So we're giving away $25 Amazon gift cards. We're also giving away an item from the LAS website of your choice, from our LAS website store. We're also giving away LAS hats. We're also giving away, this is actually really cool. Nazir made this beautiful calendar with astrophotography that he did. So he's going to be giving away one of those. Spencer is going to be giving away one of the globes that we had as a centerpiece from our last banquet. And we're giving away a laser this time, because I got the lasers finally. So there are lasers.
Blaster.
Is this that space laser that's been starting the fires?
No, no, it's not even GoldenEye.
Daryl,
It's not even a Bond movie. What the heck?
Okay, I'm going to close out the drawing now so that I can get things ready for the. I'll close out the form so I can get this stuff ready for the drawing.
Hear more from Daryl.
Okay, here we go. All right, just 1 second here. Okay, I'm going to share my screen so you can, so it'll be completely above board.
Yeah, we don't trust you at all.
We're just randomly picking names out of a hat over here,
It used to be a lot easier when we had the hat.
Okay, so you can see the screen with the spreadsheet.
Yeah.
Okay, so I'm going to drop the names in. And the first prize goes to Brett B.
Okay.
Who? Okay, let's see.
What's he getting, Alicia?
He got an Amazon gift card.
All right.
Yay.
Thank you.
Okay. Next one goes to Stam Hill.
Okay. He got one item from the LAS website of his picking.
Okay.
Yay.
Christine.
She won a LAS hat.
Okay.
Okay.
Dave Yackerson.
Yeah.
Hey, what'd you win, Dave?
I don't know yet.
Got an Amazon gift card.
Yeah,
All right. Thank you.
Just missed the lightsaber.
Oh, darn.
Okay. How
No,
many
I'm
more?
giving away that last. You want to be last if you want the laser.
Thomas Hendricks.
He won an item from the LAS website.
Okay.
Hold it. I'm still writing it down.
All right.
Got it.
Okay. And Kimberly.
Won a LAS hat.
Thank you.
How many more do we have?
3.
Okay. Carol.
I won Nazir's calendar.
Okay.
Cool.
Andrea.
Won the globe from Spencer.
Okay.
Hold on. Don't delete it yet. I'm still writing it. Okay, got it. And the last person wins the laser.
Yeah.
Greg
Right.
Thompson.
Right. I've been waiting. Yeah.
Boy. Don't get in front of Greg.
I'm gonna be duct taping it to my 10-inch Dob so I can do adaptive optics.
Hey, Greg, well, we found out what Joe and I found out is that green laser makes a fantastic finder scope.
Sure does.
Oh yeah, no, I'm into that.
In fact, we're thinking on putting one on the telescope up at Ford so we can find things a little easier at Ford.
Yeah, and getting like some big muscle guy to move it for us, right?
Well, if we got a laser finder on there, we'll be able to find things a heck of a lot easiasier.
Yeah, that would be cool. And we're talking about adding the extra telescope for imaging, right?
Yes,
That's going to be
the 6F12
super cool.
The 6F12 refractor on there as soon as we could get Jeff Schroeder to get to his hangar and get that thing put on the telescope somehow. So at least when we're looking at something through the eyepiece, we can pop a camera in the 6F12 and take an image of it.
Well, I hope we're up and running this summer, man. That would be super cool.
Well,
Alicia?
right now we're burying snow up there right now, so we're kind of stuck right now.
Would I be able to give my gift card to Birley as a donation for her? Just to talk tonight. Yeah,
Oh,
thank you.
that's so sweet.
Yeah.
Thank you.
Yeah, Briley, you can order dog treats with it. So.
Also kind of got up into chatting.
Email
We also kind of got up into chatting, and I'd
you.
like to actually thank Briley for the end of the talk. That was really wonderful. Thank you.
Yeah,
Thank
fantastic
Thank you
talk.
so much.
Great talk.
Thank you, Birley.
What'd you say,
Thank you,
David?
Alicia. Thank you.
I need her email address.
I have it, Alicia.
Oh, you do?
Yeah.
Okay. Cool. So I'll contact you for it then.
Yeah, this is old Jack out here in Denver again, and I want to thank Briley for an excellent presentation. And I also want to wish a warm welcome for our newer members that came in tonight.
Absolutely.
And Briley, you might be interested in this. I noticed your comment about a cold night to go out back in my backyard and look through the telescope. It is currently 19 degrees.
I did my undergrad in New York City. I had 4 years of cold, and I was like, I'm going back to Los Angeles. So, not my thing.
Is that cold enough for you to put your jacket on, Jack?
Yeah, it's getting close. The weekend is 5 below zero. So, and my margaritas freeze solid at 5 below zero.
Uh-oh.
Oh, wow.
The trick is more alcohol, you won't freeze.
I was just going to inadequate fortification. And Daryl, as for you, thanks for the little gift that the snail oozed out here with.
Well, good. Did that help?
See if I get that thing fired up and through Mike's wormhole.
Excellent. Excellent.
Well, according to Dr. Fauci, guys, hopefully things should start getting back to normal by June or July and the latest August, if everybody gets vaccinated, or most people do. So that hopefully outreaches might be able to start by then, I'm hoping. So
A quick survey. How many people have had a shot, at least one? Anybody yet?
I did, yes. I've had the Pfizer, yes.
I got one today.
Good. Which one did you get?
The Moderna.
Good. Okay.
I'm going
No,
for
out
the
here.
second one on Friday.
All right.
Yeah, you
Out,
heard.
out here, it's a total disaster.
Well, if it's 19 degrees, they can't get anywhere.
It
Might even
about 2
freeze
hours
solid.
at Dodger Stadium.
You don't have to worry about freezing the freezing the vaccine.
Right. For sure.
I'm just going to mention on the outreach point, as you guys know, I work with our scouting program, and we don't know for sure if it's all going to come off, but the summer camp planned in July and August may happen, assuming that things are safe and we've had our vaccines and all that stuff. And we will have opportunities for outreach each week at the camp, a big summer camp, LA Council up by Lake Arrowhead. So I will get more of that on the wire and work with our outreach coordinator.
That's great, Greg. Thank you.
Hey,
Yeah.
Kevin, this is Spencer. Did you want to say anything about that lander?
The Mars.
Yes, the Mars lander. Got to check
Perseverance.
here. Yeah, Perseverance. Yeah, we're planning to have a Zoom meeting for those who want to sign up. We'll be sending out a notice, and so we can all just talk amongst ourselves while we watch. We'll probably be watching the NASA TV feed all together.
There's a room full of them at JPL that are doing that.
Yeah, but it'll just be us.
Sounds great.
So
That'll be cool, Kevin. Yeah, get that link out.
I think we're just going to reuse the link that we used for this meeting. So just reuse this link.
Yeah.
What night is that?
During the day.
During day, Thursday.
Is it the 8th or the 18th?
18th.
I think
It's
sometime
11
around
o'clock.
11 o'clock. Yeah, 11 o'clock in the afternoon or in the morning.
In the morning. I think the NASA TV. I think that starts basically at 10 o'clock, I believe. And so there'll be probably some individuals will be telling us what to expect, and so then they'll just around 11. I think it's 11:30 ish is the expected landing.
Great.
So we'll see what happens.
I have one last thing to add for Riley. I find it amusing that she doesn't like the cold and doesn't want to go outside with a telescope. But there are many of us that are just like you that take pictures of the stars every night. We build automated systems that do all the work for us.
Yeah.
And trust me, 9 o'clock, I'm in bed and it just does its thing all night. And it puts itself to bed at 5 in the morning. And the next day I go look at the hard drive and see what images I captured.
I love that. I love that there are people that get
feel
it.
bad. We get it.
It's like going fishing.
Yeah. Richard? Yeah, we've got a guy out here that's got an observatory with automated telescopes, and he does asteroid observations. And the joke was that he programs the telescope and then goes out on a wild party, and he knows when he found something when the telescope reduces the data and publishes his paper, and he can go to bed. But he said, there's no way I can go to bed. I got to babysit these things. Telescopes are totally automated. The observatory isn't. And I don't want to wake up in the morning and find it packed with snow.
See, I'm lucky. I live in an area of Los Angeles that, number one, doesn't have light pollution, which is really weird, and weather is relatively predictable. So my scope literally sits out in the front yard, and I use it any night that there's actually, not clouds. But I go to bed. I mean, I don't I don't do anything with it past, I don't know, maybe 10 o'clock. And it just does its thing all night. Now, I've screwed that all up because I took my wide field off and put my neighbor's 10-inch Meade on, which means I just went from being really good at this to having absolutely no freaking clue what I'm doing, because wide field is easy and 2,500 millimeters isn't. So I still haven't solved back focus, you know.
Oh, yeah. Well, you guys out there in LA have very predictable weather. I think the Franciscan monks or whoever it was wrote the weather report, 300 years ago, and it still works today. Out here, we have 4 seasons, maybe 6 complete seasons.
No, in Denver,
Yeah.
you have 8.
Well, we have at least 6, but they're all at the same day.
On the same day, right? No, it's like
Bicycle. Bicycle to work in the morning in shorts, and 8 inches of snow in the parking lot by quitting time. So yeah, it's interesting around here.
Hey, Kevin, what's the weather going to be like Saturday at Lockwood? I hear it's going to be overcast. Is that correct?
You know, I earlier I started looking at stuff to get information, and I got sidetracked. So I'm sorry. I don't have it. Go to
David.
I think there's a storm coming in this weekend.
There's a storm coming in Wednesday and Friday and Saturday, and the most likely chance of snow for Lockwood is Saturday, Sunday.
Okay, thanks.
Well, so much.
I think you're going to be clouded out this weekend.
It'll be clouded out for all of us, but it might be snow.
Sounds like it.
Sounds
like it. Well, maybe one of these times when we have our summertime up at Ford Observatory, we can invite Birley up to Ford and take a look through an actual telescope. And it's actually during the summer, it's actually quite pleasant up there during the summertime. For those that have been up there during the summer, it can be quite pleasant up there during the summer. Up at
Birley,
Ford.
yeah, we'd love to have you at our star parties. Love to have you at our star parties. Love to have Birley at our star parties in the future.
You got to get out and look through a telescope.
Yeah, when I used to observe at Palomar in San Diego, even though we'd be, using the telescope inside, it was really nice to go stand out on the catwalk of the telescope and look outside, especially in the California summer. Then I could do it.
That's good. That is good.
Can't beat that.
Okay, guys. It looks like we can probably adjourn the meeting. So some of us, like Richard Horn, can go to bed since he goes to bed at 7 o'clock. It's almost there now. And of course, Jack over in Denver, it's 11:30 over there now, right, Jack?
Yeah. One other comment about observing under conditions. I remember observing out on the patio of my Aunt Lisa in Cathedral City. And I'd get up about every 10 minutes and take about 10 steps backwards and fall in the swimming pool. And about 1:30 in the morning, I decided I'd had enough of this, and I checked her thermometer. It had chilled down to 105 degrees at 1:30 in the morning.
Yep.
Just the opposite of what I've got outside here right now, which is now 18 degrees.
I spent a couple years in Arizona after I left Warner Brothers, and I will never forget the day that I got out of the shower and I walked out to my little patio over the golf course at the condo, and I looked at my little hydrograph set up on the wall, and it was 122 degrees at a 100% humidity.
Oh, whoa, God.
And people talk to me about Florida, and I laugh at them.
Yeah, I got an invite to a job interview in Dallas, Texas in August. And I'd been sponging off my favorite aunt, and 118, 120, no problem. And they kept telling me, make sure your air conditioners work, and on and on and on. It's hot. And I checked the weather forecast the weather out there? 95, 96. Holy cow, I'm going to take a sweater. Well, I got off the plane and I thought I was going to croak before I got to the terminal. It was like 96 degrees and 96 humidity. And out of my aunt's place, if it was more than 10% humidity, we were in trouble. So yeah, the humidity will kill you.
Like that every
Okay,
time.
well, anyway, guys, I think it's, we can go ahead and get ready to adjourn the meeting, and everybody who wants to stick around and talk afterwards, you're welcome to do it. I think the Zoom meeting is probably, the Zoom link is going to be, well, Spencer, how long are you going to keep the Zoom link up and going?
Okay, I'm going to stop recording now, and I'll leave the Zoom session open for until 10 o'clock. Then I'll close it down.
Next board meeting is going to be when? March when? For the next board meeting?
March 3rd. March 3rd.
Thank you.
Thank you again, Birley.
Okay, well, I'll go ahead and adjourn the meeting then, and we're done for the night. Thank you, Briley, for the great presentation. Appreciate that.
Thanks for having me.
Both thumbs up.
Thanks.
Yep.
Awesome.
Thank you.
Wonderful report.
Wonderful. Excellent.
Thanks so much. Good to meet you all, at least over Zoom. So
Yeah.
hopefully
Yeah,
see each other
thank
in
you.
person someday.
Hopefully in person.
Thanks again, Briley.
No problem. Have a good night, everyone.
Good night.
Good night.
All right.
So Spencer, I got interviewed recently by the Peninsula magazine.
Oh yeah, you told us about that.
Haven't seen.
If you get Peninsula, it came out. It's an
I rattled
interesting
the
article.
chain, but it didn't work.
Interesting article because it didn't end up being an article or an interview about astrophotography as much as it turned into like a memoir. It was very weird, but all the pictures are astro pictures. But they did not use the picture where I was wearing my LAAS hat. I was kind of bummed, but it was funny because they did the article because of the conjunction, and the publisher of the magazine knows somebody that knows me and decided to do an article because of the conjunction. But my conjunction picture was horrible. I'm not a planetary guy, so it's like, what the hell? I don't know if you can see this.
I don't know.
Yep.
You have to turn off your background, or it's.
I know. Oh, wait, okay, there we go.
Yeah, it's hard to see.
Well, it's a horrible picture.
It's not gonna work.
Yeah, it's not gonna work. It was not that great because I'm not a planetary guy. So I literally used my my Nikon with a 600 millimeter lens and did video, set up one for Saturn and one for the other, Jupiter, and then I ended up combining it. It's mediocre at best. Okay, it's not a great picture, but it's like, it's an article about that, and it's like, really? But then I read the article, they didn't talk about astro at all, really. It was like yeah, it was weird. It became like a my history of my life, with pictures of the stars. But it's what I guess
You
what
never
they decided
know.
was fun.
Yeah, you never know what's going to happen. I've been interviewed several times, and then I look at the article or whatever, and it's like, wow, did I say that? I don't
Oh, totally. Yeah, that was it.
LA Times, the Los Angeles Times once quoted me. They decided to compact the text so that it would fit better. And so when I said Griffith Observatory would be the world's premier public observatory when it was finished, they just took out the word public and quoted me as saying Griffith would be the world's premier observatory once the renovation was finished. And I was still working at JPL at the time in a room full of astronomers. They all read it before I got there. You should have heard what I was in for when I got to work. Griffith Observatory. Ah, boy.
Well, Tim, did you watch the Super Bowl?
No, I did not.
Okay,
I have not.
there are two commercials There are 2 commercials you have to go onto YouTube and find, just because of what you just said. Go find the T-Mobile commercials. You will you'll laugh your ass off. It's everything you just said. Because what they do is they take a normal conversation and they record it, and then they take it and say, here's what he actually heard because he was on a bad network. And they
I saw this.
And
Yes.
it edits what was really said. It's brilliant because it literally, it takes Tom Brady retiring and he's in a phone call with his buddy Gronk. Oh God, help me. Somebody.
Whatever.
Thank you, Gronkowski. Okay, so he's on a phone call with his buddy Gronkowski, and Gronkowski says, dude, you should retire, have a safe life, have fun, come to Florida, hang out, on the sand, blah, blah, blah. And I'll even come with you. And then what they do is they backtrack and they say you had a bad connection, and it edits it because the phone was screwing up. And it ends up saying you're gonna come to Florida. If you don't come to Florida, if you retire, you're soft. You're a pussy. You're gonna He goes on and on. So you gotta come to Florida and play again. And you know what? If you do it, I'll come with you. And so it turns one conversation into another. It's the funniest thing you've ever seen. Yeah. Brilliant. And it's exactly what you just said, and it's exactly what I thought about my article.
Okay, guys, this is Spencer. I'm gonna bail. Have fun.
Okay. Thanks, Spence.
Spence, you did stop recording, right?
Oh yeah, I've stopped.
Oh, good. Thank God.
Oh, it still says live on YouTube.
Alicia,
yes.
Alicia, tell me about all the jets you have behind you. What's the interest in the flying back there with the?
Oh, they're